In this video, we'll take a look at the ADALM2000, also known as M2K, and its ability to generate and view small signals. And by small signals, I generally mean signals of 100 millivolts peak to peak or less. We'll do most of the tests with a 50 millivolt peak to peak sine wave. To generate the signals, in addition to the M2K's signal generator, we'll use this analog Wien bridge oscillator. It's set to produce about a 2 kilohertz sine wave, and the potentiometer on the left can control its amplitude, which will be set to produce a sine wave of approximately 50 millivolts peak to peak. Here's the schematic for the Wien bridge oscillator. I wouldn't copy this. There are a few things that I'd change about it, but it's what's being used. The M2K signal generator is set, like shown here, to generate that 50 millivolt peak to peak sine wave of exactly 2.113 kilohertz. That's to match the frequency that the Wien bridge happens to have. Notice that the output impedance is set to accommodate 50 ohms. That's because we're using this 50 ohm coax to connect the M2K to the Siglent oscilloscope. So the Siglent oscilloscope is set, for a 1x channel. And that's important for small signals. If you used a 10x probe, the already small signal would be divided by 10 in amplitude and then would just have to be amplified by the oscilloscope, and that adds noise. So it's better to use 1x, provided the band or the signal frequencies are low enough that you can live with the bandwidth limitations of 1x probing. The Wien bridge is connected to the Siglent oscilloscope just using a normal probe with its flying ground lead. Remember, the frequencies are small here, and that channel is also set to 1x. Here are the two waveforms. The pink is from the analog Wien bridge, and the green is from the M2K. You can see by the cursors that both of those sine waves are approximately 50 millivolts peak to peak. The frequencies are close to matched, but the one drifts with respect to the other. That's and the Wien bridge itself is going to be a little bit less frequency stable. So these are both shown with full bandwidth on the Siglent oscilloscope. Let me switch the two channels to 20 megahertz. So there's that one, and there's that one. That kind of gets rid of some of the high frequency content and maybe makes this a little bit more easy to see. And getting screen captures from the oscilloscope is probably even providing a slightly better picture. So we'll switch to that. Here's the still capture. They're both pretty good sine waves. In fact, in the previous video, you could see when they happened to line up in time, they were nearly identical. The big difference is that the M2K signal generator is using a digital to analog converter, so it's only capable of producing certain discrete voltages. I believe it's a 12-bit DAC, so it should be able to produce 4096 voltages. And I think we're seeing the effect of that here. The M2K signal looks jagged compared to the one from the Wien bridge. For comparison, here's the Scopy oscilloscope view of the same thing. Channel 1, the orange, is the Wien bridge, the analog Wien bridge, and channel 2 is the M2K signal generator just connected to channel 2 directly. There's no breadboard involved. These are just point-to-point connections made with jumper wires in both cases, actually. I think that it's harder to tell the signals apart than it was with the Siglent oscilloscope, but channel 1 does look a little bit smoother. It seems pretty clear that the Siglent's higher sampling rate and probably more advanced filtering and interpolation helps. So the Siglent view is quite a bit better. There's also, the issue of the sampling rate is significant. The Siglent was sampling at a giga sample per second. This is sampling at 10 megasamples per second at the moment. Scopy software just tries to pick the sampling rate that it thinks is best. I don't know that there's too direct control over that. You can change the let's see, I think you can change the memory depth, but I think that'll just make it worse. Yep, that just makes it worse by picking up more noise. So anyway, that's what the Siglent oscilloscope shows for the two channels. To end, let's go back to the Siglent viewing the output of the M2K signal generator. Here's a 20 millivolt peak-to-peak rising sawtooth waveform. The effect of the DAC and the kind of the quantization you get from that seems very obvious. Here's the same, but with a 50 millivolt peak-to-peak signal, so there are more steps. You can in fact count the number of steps and divide that into the 50 millivolt range and try to get an idea of the voltage of each step. This doesn't lead to a result that makes an incredible amount of sense to me. I get about 1.8 millivolts per step. That seems to be a little small given the M2K's output range, so I'm not sure about that exactly. And here's a 100 millivolt peak-to-peak rising sawtooth. So I think I'll end here. In summary, I think that the M2K is not all that great for producing and viewing very small signals. You might consider yourself limited to 50 or 100 millivolts peak to peak. I hope you found this interesting. Thank you very much.